Inspired by infants that repeatedly attempt to grasp a toy until they learn reliable ways to grasp it, we consider a novel problem, exploratory grasping, where a robot learns to reliably grasp an unknown object through sequential grasping, releasing, and toppling. We then present an asymptotically optimal algorithm for discovering high quality grasps in this setting, which leverages insights from general purpose grasping systems. Prior work leverages recent advances in machine learning to develop general purpose grasping systems that achieve high grasp reliability on a variety of objects. However, these systems can struggle to grasp some challenging objects which have out of distribution geometries or very few high quality grasps. We formalize exploratory grasping, a new MDP formulation for grasp exploration. We leverage the structure of the resulting MDP to provide bounds for a family of tabular RL algorithms. And we present BORGES, a new grasp exploration algorithm with desirable theoretical properties. Simulation and physical experiments suggest that BORGES can substantially outperform prior algorithms on a number of challenging objects. The idea of exploratory grasping is to explore grasps on the stable pose of an unknown polyhedral object to learn a policy which can robustly grasp the object when it is dropped in front of the robot. We formalize this problem as an MDP where each object is a state and k grasp actions are sampled on each stable pose. The agent receives a reward of +1 if a grasp action succeeds and 0 otherwise. In practice, BORGES performs well on a wide range of polyhedral objects. However, the theoretical model makes 4 assumptions. When a grasp succeeds, the robot can lift and release the object into a random, possibly new stable pose. When a grasp fails, the object may topple into a new stable pose. The robot is more likely to transition between a pair of poses by grasping rather than by toppling, and there exists a grasping policy which can reach all stable poses with non-zero probability. We quantify the theoretical complexity of the exploratory grasping MDP by bounding its diameter, a measure of the furthest distance between pairs of states under an appropriate policy. Recent work then allows us to directly formulate diameter-dependent regret bounds for a family of tabular RL algorithms. It is typically difficult to interpret an MDP's diameter. However, for exploratory grasping, we show that the diameter can be bounded as 1 over the product of epsilon, which is a lower bound on the success probability of the best grasp over all stable poses, and lambda 1, the minimal landing probability over all stable poses. Intuitively, grasp exploration should be more difficult if grasps are of lower quality or if there exists a stable pose which is difficult to reach. These tabular RL algorithms have intuitive theoretical guarantees for exploratory grasping, but they do not leverage problem structure, which leads to inefficiencies. Our key insight is that most objects have a small finite set of stable poses, so it may be more efficient to learn these pose-specific policies rather than just learning one policy. Driven by this idea, we present BORGES, the Bandits for Online Rapid Grasp ExplorationStrategy, which exploits geometric structure in the problem and defines a policy for each stable pose by running a no-regret bandit algorithm for grasp exploration on that pose. The name is inspired by the famous writer Jorge Luis Borges, many of whose short stories leverage clever geometric ideas. Given standard technical assumption, we can prove that BORGES achieves vanishing asymptotic static regret for the exploratory grasping problem, and we implement BORGES using Thompson sampling in the UCB1 algorithm, 2 popular no-regret algorithms for bandit exploration. We evaluate BORGES with extensive simulation experiments. Consider the following pawn, which is very challenging to grasp due to its irregular geometry. We compare BORGES with Dex-Net, a state-of-the-art general-purpose grasping system which is fine-tuned online, and UCRL2, a tabular RL algorithm. We evaluate 3 variants of BORGES using UCB and Thompson sampling with both a uniform prior and a prior that uses initial Dex-Net grasp quality estimates, labeled as TS5. We plot learning curves for BORGES and baselines and find that BORGES converges to the optimal policy, which knows the best grasp on each pose in advance more quickly than baselines and can efficiently leverage priors from general-purpose grasping systems. Additionally, we evaluate all algorithms across a set of 46 challenging objects and find that BORGES rapidly converges to near optimal performance. In initial physical experiments, we find that BORGES' ability to explore online and rapidly learn from grasp outcomes yields a 45% improvement over Dex-Net in grasp success rate with just 200 attempts on a real robot for 2 challenging objects. Thank you for listening, and please see our website for more information. We invite you to collaborate with us on extensions. Please feel free to contact us and join our interactive session on Wednesday from 12:30 to 1 p.m.